This video will study work. We can say basics of work. Work is said to be done when force displaces where it is acting, or force displaces its point of application. In other words, when point of application of force is displaced, work is said to be done. Okay. Again, the important word is point of application of force. It should move. Okay. So only then work is said to be done. Small work is defined as F dot ds. F is nothing but the force vector. Ds is the small displacement of point of application of force. You can also say F ds cos theta, where theta is the angle between F vector and displacement vector. So to calculate total work, just integrate that. And if force is constant, it can be taken out, and integration of ds will be delta s, which is nothing but the displacement. As displacement is a state dependent, or we can say path independent quantity, so work done by constant force is also a path independent quantity or state dependent quantity. It depends only on what is the initial position and what is the final position, and not how you are moving from initial to final position. Okay, so let's start with the first example. There is a block of mass m on which these forces mg, f, there's a constant horizontal force, normal reaction and friction are acting, and the block slides down by a distance L. We have to find work done by each force. Okay, work done by each force. Let's start with normal reaction. Work done by normal is simply 0, because normal is acting in this direction and displacement is this. So the angle between them is theta is 90, so the work done is 0. Okay, let's talk about work done by friction. Work done by friction is acting in this direction and displacement is this. So the angle between them is theta is nothing but 180 degree, and we write friction into displacement into cos of 180. So we get minus friction into displacement. Okay, theta is 180. Let's talk about work done due to mg. Work done by its weight. Weight is acting downward and the displacement is this. This is force, this is displacement. The angle between them is 90 minus theta. Okay, this is theta, this will be 90 minus theta. So we can say work done is mg into L into cos of 90 minus theta, which is mgl sin theta. There is another way of getting the work done. Work is component of force, component of F along displacement into displacement. Okay, so what is the component of force along incline, which is mg sin theta, into displacement is L. Okay, so let's take the similar method to calculate work done by F. The component of F in this direction, in this line, this is F and this will be F cos theta, as this angle is theta. So we can say component of F along the line of displacement is F cos theta, and the displacement is L, but they are opposite, so we get a minus sign here. So work done by F, force F, is F cos theta into L. We can also say that this is force, this is displacement. The angle between them is pi minus theta. So according to the definition, F into L into cos of pi minus theta, we get work as minus FL cos theta. Okay, so now we have two definition is Fs cos theta or component of force along displacement into displacement. Okay, there's an interesting thing, we can take the component of displacement along force, but these two approaches are quite same. In the next example, a particle is displaced from point A, which is 1, 2, 3, to B and then to C by applying this force. As the force is constant, we can simply take out the displacement and take the dot product. We have to find work AB. Work AB is force into displacement. Displacement A to B is nothing but F dot final position, which is position of B minus position of A. Okay, the dot product will give you 3i minus j plus 4k and RB, which is 3i plus 2j plus k minus RA, which is I plus 2j plus 3k. Okay, so getting their dot product is nothing but this will give you 3i minus j plus 4k dot, this is 2i, 2j will cancel and we are left with minus 2k. Taking the dot product, I will get how much? 6 with a minus 8, so minus 2 joule, no matter how we are moving. And work A to C. Again, the work A to C is independent whether we are moving via B or via any other point. It simply depends on force and displacement A to C. Force is again 3i minus j plus 4k and displacement A to C. C minus A is 3i plus 2j plus k. I have taken the difference orally, so we'll get 9 minus 2 plus 4, which is 13 minus 2, 11 plus 11 joule of work. This is joule. What if a force of minus kx acts on a particle and it displaces from x1 to x2? Again, we can say the force is variable, so we have to integrate f dot dx. The force is minus kx dx. Again, from x1 to x2, we will get minus k common, x square by 2, putting the limits as x1 to x2. We will get w is equal to minus k by 2 x2 square minus x1 square. This is nothing but potential energy stored in a spring, because spring force is given by minus kx. We'll talk about it later. For the time being, we can say this is nothing but minus delta u of spring. Okay, we'll discuss this point in the video of potential energy. Find the work done by F and friction. There's a block which is placed on a rough surface having friction mu and it displaces by distance x. So we have to find how much work is done by F and the friction. So again, work done by F is simply force into displacement x, and force and displacements both are in same direction, so the angle is cos 0. So the work done is nothing but Fx. But for work of friction, to calculate work of friction, you can say friction is acting here, which is mu mg, and displacement is opposite to that, so theta is 180 degree. And friction work done by it will be friction mu mg, displacement, and cos of the angle between them. So it will be minus mu mg x. Okay, enjoy.